we are hoping that will be same as equivalent, but in real situation there will be a slight difference, but that is okay, right? And then when you titrate all the way to completion, that equals point. But if you are in the midway, exactly in the middle of titration, then we call the midpoint. So at midpoint, we are putting only half of titron that we require to completely neutralize analyte. There's a halfway through equals point. That's what we call midpoint. Let's say we titrate a strong acid, like here you have only HCl down here, HCl, and you titrate with NaOH. So initially you have strong acid only. So when you have strong acid, you can calculate pH based on negative logarithm of concentration of acid, right? So if you determine pH, you may have pH something like very small, like 1. So from this graph, you know concentration must have been 0.1 molar concentration, right? Now when you add base, because you are using up, you just use up acid, you have less hydrogen concentration, so this will drop because you titrate some of those, so it drop. If it drop, pH should increase. So your x-axis is amount you put base. So pH level will move up until endpoint. At endpoint, you put exactly equal amount of hydrogen concentration, hydrogen ion and hydroxide, then it will be neutral. So that's why endpoint, equivalence point will be pH 7. Okay. So here you have just an acid base, acid or base, in this case acid situation in the beginning. At the end of titration, you have salt, because you do not have acid, you do not have base, you will have salt. So here it will be salt problem. Any point in between initial and final is a buffer. I'm sorry, this is not buffer yet, because this is strong acid, strong base. I have to say that on the next slide. So all you have to know here right now is at the end point or equivalence point, that will be pH 7 because it's strong acid and strong acid. After equivalent point, because you are putting more of base, pH will rise up all the way to concentration hydroxide. Okay. Now we're going to compare this one with weak acid and strong base case. Instead of HCl from previous slide, this is a weak acid, acetic acid. Because of that, concentration of H plus will be a lot less. Because a lot less, pH will be higher. So that's why the initial point here, graph is higher than 1, right? Because it produces less hydrogen ion, starting point will be higher. This is comparing this black line is strong exit, there are other kinds of weak exit. If you compare it, it starts higher, and also if you look at the slope for weak exit is almost steeper, okay, compared to this. The reason is that when you neutralize strong exit to base, once you neutralize it, that guy become water. Okay? When I have weak exit, by the way, and then neutralize same amount, then it not only neutralize but also produce conjugate base. So when you compare those two guys, even if you neutralize like 10% of each, this guy you have additionally have weak base, conjugate base. So this extra will make it even more basic. So that will make it pH rise a little rapidly. So when you have a weak base titrating by weak acid, this will increase a little more rapidly. That's why slope for weak acid is a little, relatively rapidly changing compared to weak strong acid. Okay. Now, this will be a weak acid problem. You're gonna use ice table. This is salt. In this case, weak acid and strong base. So you're gonna use salt problem with ice table approach again. But this is where it is buffer. In the region between E. So you're gonna use a buffer approach. Okay.
Can you say that last part one more time? The buffer approach.
So when you have analyte only, that will be just weak acid. So you use ice table to deal with this problem. And then if there's end point, equals point, you do not have acid or base, you have salt.
Okay.
But to solve salt problem, you're gonna have another ice table. In between you have acid and titrated, some part of it with strong base. This guy turn into conjugate base. So you have both acid and conjugate base together. It will be just different ratio depending on which region you are looking at, but it will be buffer anyway. All those paths is buffer with a different pH. Okay? So you're gonna have to use buffer pH. Right. Again, back to strong acid, strong base titration. Let's say I have this much of acid. I'm titrating with strong base. If we didn't add any base yet, then you only have strong acid. So pH for strong acid is negative logarithm hydrogen concentration. So negative log, and then concentration of acid is 0.05. Right? So if you do that calculation, you're gonna have this number. But if you add 10 milliliters of sodium hydroxide, then we have this guy, 50 times 0.05, which means, what is it, 50, 2.5 millimole. And and you are adding 10 milliliter of that guy. 10 milliliter of this. So that means 1. 1 millimole. So because this will neutralize part of it, remaining amount, remaining H plus is from subtraction 1.5 millimole. Remaining H plus is 1.5 millimole. So concentration is 1.5 millimole divided by total volume. You're adding 10 milliliter to 50, so there is 60. 0 milliliter. So you have concentration 1.5 divided by 60. 2.5. So pH is a neutral of that number become this. Why don't you try CND yourself? C is simple, right?
I think it should be larger, actually. Cause you're adding
Should
50 plus
six-
30, right?
Yeah, should it be 80 milliliters instead of 60?
Oh, D. Yeah, D. Who said that?
It's him.
Any question? So I want you to be comfortable with each stage of titration. Okay. Is it okay if I move on to the next slide? Do you need more time? Can I erase this stuff here? Is it okay? Right. So that was we have actually say in the analyte, and then you have titrant of NaOH. We could have opposite situation. So if this is NaOH in the bottom, now initial pH will be very basic, so number is very high up here, and then you start putting acid as titrant, then pH will drop. So basically this is same drawing with on just flip left and right side. No, actually upside down. Okay? It was very basic, and the equilibrium point pH will reach to 7, and later once everything is done, equilibrium is 7. If you add more of acid, then pH will go down as very acidic. Same principle. Now, when you titrate weak acid to strong base, you should identify so certain amount of weak acid mixed with certain amount of strong base. You're going to decide is the buffer region or equivalent point or after equivalent point, because depending on the phase, you need to approach a little bit differently. Okay? So we have weak acid like acetic acid here. Acetic acid. And then if we didn't add any NaOH yet, then you have just weak acid. Because weak acid, pH will be just for weak acid, what do you do? How do you determine pH of weak acid? This is like a review. So you did weak acid, buffer, salt. So this will be review. You have weak acid. How do you determine? Ice bath. Because weak acid, you use ice baths. So we have 0.10 weak acid. So certain amount dissociate that you create that much. So K A is x squared 0.10 minus x. You can approximate at 0.100 x squared. So x squared will be that times 0.100 inside square, that's your x. X is our passive concentration. So my pH, which is relative low H plus, is relative low of square root 0.100 Ka. So if you do calculation, you're gonna get that number. Just weak acid. You had 10 milliliters of sodium hydroxide. Do you recognize this is buffer now? How do you know that's a buffer? How do you know this is a buffer?
Because you're adding a strong base to a weak acid.
Yeah, you are. So you have to say more. That doesn't make it buffer yet.
Because you're adding a small enough amount of strong base that is converting some of the acetic acid into its
Yes. Yes.
contribution.
You are adding strong base to weak acid, but you are putting less amount compared to weak stuff. Then make a buffer. So you see this as a buffer because you know buffer. What do you do? How do you find the pH then? If you identify, because you just identify, oh, this is a buffer. It's a Henderson-Hasselbalch. Yeah. But you can still use equilibrium approach, stoichiometry altogether, but Henderson-Hasselbalch make it simple. So for B, pH, pKa. pKa is already, we already know, they didn't give you, so you're gonna have to look it up. Table. So, what is it? Because you have to look it up anyway. 1.8 10 to the minus 5, right? Let's find out that number. Now logarithm HAA minus. Which concept of acid? Right there. Do you use this number? No, you cannot use this number.
Multiply it by the millimeters.
Yes, very good. We need consensus reaction. Consensus given, we cannot use this number because that was before adding base. Once you add base, this concept will change. So you have to find out. So what is HA then? Well, HA will be total constant, total volume. Total volume will be 10 milliliter plus 50. So it will be 60 milliliter. In 60 milliliter, now you have to find out how many more of X are there. Well, initially, you multiply 5 millimole. 5 millimole. 5 millimole. But out of 5 millimole, you are losing 1 millimole. You are losing 1 millimole. Okay. So I have 4 over this. Which means 666. By the way, I'm not going to continue because there's a reason. Alright, let's put just like that. What about A minus? Conjugate base is, actually I don't have to do this but now, volume. And then conjugate base is, originally I didn't have conjugate base, but because you are adding 1 millimole, we will get 1 millimole of conjugate base. So I can put this concept here, but thing is 60 milliliter is a common factor. So you can just put HA as 4.0 millimole and A as 1.00 millimole. Why? It should have been concentration, but you have a common factor, they will cancel each other. So you don't have to put it there. So for C, we originally had a HA. Originally, this guy we have how many more? We have five minimum, right? 5 minimum. And then we are adding hydroxide. How many more? 25 milliliter, 0.1. And make it 2.5. So remaining, this is now 0.5. Okay, more. And then you have a hydroxide, now 2.5 milliliter. So you know that the initial amount is 5.00 millimole, but when you recognize hydroxide amount is 25 milliliter, you realize that it will be half of what you have. So half of that will neutralize, and that turn into conjugate base, but still you're gonna have remaining half amount, 2.5 millimole of action. When you have equal amount of X and conjugate base, then you have equal amount X and conjugate base, then in the equation, this ratio become 1, and you have, this will become 0. So pH will be just pK. Okay.
Will that always happen?
Hmm?
Does that always happen?
Yes, if that's equal amount. So this is what we call a midpoint, at midpoint. At midpoint, pH will be just equal to pK, always. So we start with, we had actually there's 5.0 more millimole. And then D, now you adding 50 milliliter sodium hydroxide, but concentration is still this guy, so you can multiply 50 times 0.1. 50 times 0.1, then we have exactly 5 millimole. So all of FC is completely neutralized. So you had this before, but after neutralization, you have nothing remains, and then you have conjugate base 5 millimole. So this is just a sort problem, okay? Because you have conjugate base of this amount, then that guy will start hydrolyze in the water. This. And then we know this is 5.00 millimole inside of volume. Total volume is what? What is it, total volume? 100, because we had original 50 milliliter solution, yeah, you had 50 ml of other solution, so 100 milliliter. So our concentration is just milli cancel, and then molar 0.05. This is our initial condition of isotable. And then at equilibrium we have this minus x, xx. And because it's conjugate base, which base is the kb, and x square, which means which minus square over 0.0500, which approximation. So my hydroxide concentration is inside of square root kb times 0.0500. So kb value is not given over there. You're going to have to do 10 to the negative 14 divided by Ka value. And 0.05. And the Ka value is already given as 1.8 minus 5. Then if you do calculation, you're going to get that pH, not that pH. Inside of square root, where is square root? 14 divided by 1.8 minus 5 times 5 plus 7.906 into negative 6. So pOH of this number, negative log of that number equal negative log of that number. Okay. 5.10. Something not
Got 5.28 for the hydroxide concentration.
I got the same
where,
thing.
5.27 times 10 to the negative 6 for the hydroxide concentration, not 7.906.
7.9.
So instead of 7.906, I got 5.27
Oh, okay.
times 10.
Okay. So I did something wrong. Thanks. Inside of square root 23 14 divided by 1.8 5 times 0.05. Yeah, that was wrong. Thank you. number 5.2704. Okay. So negative log of that, negative log of that from 5 to 7, 5 to 8, 5 to 8. That makes sense. And Q. Now in terms of sigma, how we get there? Because that's 2 sigma. Yeah, because this is 2 sigma. This is 2 sigma. This is 2 sigma. That's good. Is it okay if I erase this A? I think it should be okay by now. Okay. Yeah, all right. A is gone.
So then do we not subtract that from 14 to get the pH?
We do. I just, because answer was there.
Oh, okay.
Yeah, obviously now 14 minus 0, 0, 5, 10, yeah. So answer will be A7. Yes, we should. E. We still have same initial amount of acid. HA is still initially 5.00 millimole. Now we are adding how much of base? Well, from when you did the question D, you knew if you put 50 milliliter, that will completely neutralize, right? So that extra 1 milliliter will provide extra, which means you're gonna have 5.10 millimole. Why? 50 milliliter completely neutralize that. So you're gonna have OH minus this much. So altogether, after you neutralize, no, all of them will be neutralized to this, and then you're gonna have leftover this guy. So in terms of concentration now, total volume is 101, right? 101. So this concentration is 101 A minus. So once you find out, after neutralization, you have strong acid and strong base this much, and then conjugate weak base this much. Which one is more important? Between two. So you have in this solution, you have a little amount of strong base, a lot more of weak base. Which one will come in pH? What do you think? How you're right?
Because I used that one and I got the right answer.
Okay, alright. So POH, if we just use this guy, it will be negative logarithm of this number. And there's another set, you got answer as
I got like
the
3.
3, right? 300, so which you make it this guy, right? But then, okay, that's your answer. But the thing is, you also have weak base in your system, right? So this weak base will hydrolyze water. So you have both of them. This will hydrolyze water and produce another hydroxide, right? But the thing is, how much this guy will produce hydroxide? Now we know that pK, so if it's pK or kb of A minus, kb of A minus is 10 to the negative 14 divided by Ka, and the Ka is 1.8 10 to the negative 5. So if you do math, it will be something like 10 to the minus 10, something 10 to the minus 10. So even though we have a lot more of weak base, a lot more than that, this number is small. Actually, D was the situation. In D, we have exactly the amount of base, and then that gives us pH value, this number. Okay? This is when you do not have extra strong base. Everything turns into conjugate base. The conjugates will give you pH value this guy. Here, not including weak base, only considering extra strong base will give you pH as that value. So in terms of pH 3, in terms of pH it was this. So if you compare hydrogen concentration, this will be 100 times more. So obviously both strong base, extra strong base, and converted weak base will produce hydroxide, but this will be 100 times more than that. That's why you can ignore something like 1% stuff. So when you face this problem, you just assume you can just ignore. You can ignore weak base. Although you have both, I don't want you to go through all those calculations. Just assume this will be negligible compared to that guy. So just calculate continuum from strong base only. Okay? It's okay to ignore that guy. We are not going to treat you with a larger number of A minus that will be comparable to strong base. We are not going to do that.